Hello everyone and welcome back to Fun Physics Problems. Today we're going to look at problem number 3 and here it is. So we're going to try and rederive the expression for the relation between acceleration, velocity and the radius in circular motion. So I think let's dive right in. So this is of course the expression we're going to try and derive, and this is the scenario. So this is just a visual illustration of what's going on. So in a circular motion system, you have the velocity going like this, the acceleration, which represents the centripetal force, and the radius of the circle along which the motion is taking place. So let's start by writing out some of these some of these vectors in terms of their constituent components. So we know that r is just the whole root of x squared plus y squared, and note that we're considering this point as 0, 0, so that's just the origin. We know that v is going to be vx squared, the root of vx squared plus vy squared, and a is just going to be the root of ax squared plus ay squared. Now you'll also notice that our x coordinate can be written as r cosine theta if this is the angle theta. This is because if we construct ourselves a right angle triangle here, then the x coordinate is the opposite side, and we know that r is the hypotenuse, so cosine theta, which is opposite over hypotenuse, times the hypotenuse is just going to be the opposite, or x. And a similar thing with the y, but y is the adjacent, so it's just going to be r sine theta. So we know that x is equal to r cosine theta and y is equal to r sine theta. And so now we can work to re-express all of these. So we know that r is just going to be the whole root of r cosine theta the whole square plus r sine theta the whole square. V is just going to be we know that Vx, by the way, is just dx by dt, and Vy is just dy by dt. And we also know that Ax is equal to d2x by dt2, and Ay is d2y by dt2. And so we can write this as d by dt of r cosine theta the whole square plus d by dt of r sine theta the whole square. And similarly we can write a as the whole root of d by dt2 of r cosine theta the whole square plus d by dt2 of r sine theta the whole square. And so I think now we have enough information so that we can start writing this problem and try and rederive a. So let's start by writing out v squared by r. So if we just leave r as it is for now and we write v squared as just taking this expression here, d by dt of r cosine theta square plus d by dt of r sine theta the whole square, and in the bottom we just leave it as r for now. Then this expression comes out to be d theta by dt, and the derivative of cosine is obviously negative sine, so negative sine theta times r, and we square this, plus d theta by dt times cosine theta times r the whole square, and we divide this by r. And so now we can write d2 theta by dt2 times r square. And then, so when we square negative sine theta, it becomes sine square theta plus cosine square theta from here. And we just have r in the bottom. So because this just goes to 1, and we can cancel the r's, so this is just d2 theta by dt2 times r. And we can now take the root, we can now put this under a root, so we can write d4 theta by dt4 r square. And if we multiply it by sine square theta plus cosine square theta, then that will obviously just be the same thing because this is just 1. And so now we can write this as d2 theta by dt2 r sine theta the whole square plus d2 theta by dt2 r cosine theta the whole square. And you'll notice that d2 theta by dt2 of sine theta is just going to be d by dt2 of sine theta. And that is indeed what we have. So if we just rewrite this expression as d by dt2 r sine theta square plus d by dt2 r cosine theta square, that is exactly the expression for acceleration we have earlier. So we have now proven that a is equal to v square, or why don't we just is equal to a, therefore a is equal to v square by r, and we have proved that. Thank you for watching, and if you're interested in proofs like these, please mention it down in the comments and I would be glad to do more of these.